Hello everyone, lecture 13. We will discuss the diagonalization of a matrix, how to diagonalize the matrix. Before starting the diagonalization, first we have to know the similarity of a matrix. So what is similarity of a matrix? Suppose we have a two matrix, capital A and B, we are square matrix of order n. Then we can say A is said to be similar to B if there exists a non-singular matrix P of order n such that A is equal to P inverse B into P. Here, the transformation of matrix B by a non-singular matrix that P to A is called, this transformation is called similarity transformation. And the matrix by which the similarity transformation is performed, that matrix P, is called similarity matrix. Here, we have to note that if suppose X is an eigenvector of B corresponding to the eigenvalue, any eigenvalue lambda, and we say A is similar matrix to B, then Y is equal to P inverse X is what is an eigenvector of A corresponding to the eigenvalue lambda. Now, what is diagonalization of a matrix? So a matrix A is said to be diagonalizable if it is similar to the diagonal matrix. So thus we can say a matrix A is diagonalizable if there exists an invertible matrix P such that P inverse A into P is equal to D. So here D, and where capital D is what is in diagonal matrix, and also sometimes we say is a spectral matrix of A, and that P matrix is called model matrix of A. That P is what is in model matrix, and that D is what diagonal matrix. So you have to remember, if we want to diagonalize a matrix, so we take it is just a similar to the diagonal matrix. So we take P inverse A P is equal to D. Here you have to note that if geometric multiplicity of eigenvalue are equal to algebraic multiplicity of the eigenvalue, then matrix is diagonalizable, otherwise not. So you have to remember, if the geometric multiplicity of the eigenvalue of that matrix is equal to algebraic multiplicity of the eigenvalue of that matrix, then we can say matrix is diagonalizable. Now, what is model matrix? As we know, we required the model matrix to diagonalize a matrix. So, a matrix which formed or obtained by the eigenvectors. Suppose we take three eigenvalues lambda 1, lambda 2, lambda 3 eigenvalues corresponding. The eigenvector says x1, x2, x3 for any matrix such that x1, the vector x1, x1, x2, x3, and x2 vector is y1, y2, y3, and we take the third vector x3 eigenvector z1, z2, z3. So x1 is a eigenvector corresponding to lambda 1, and x2 is the eigenvector corresponding to lambda 2, and x3 is an eigenvector corresponding to the eigenvalue lambda 3. Then what is the model matrix? Model matrix is formed by the eigenvectors. So we just write the x1, x2, x3, that is the x1 vector, this is x2 vector, and this is x3 vector. Or sometimes we just write x1, x2, x3. So a matrix which is formed by the eigenvector is called model matrix, and this matrix is required when we diagonalize a matrix. So here one important term we use in the diagonalization, that is power of a matrix. So by using the diagonal matrix we can obtain the power of a matrix. So here, as we know, the diagonal of a matrix is what D is equal to P inverse A P. Here P is what the model matrix and D is what the diagonal matrix of A. So if you want to find the D square, so we write P inverse A P, P inverse A P. Here the P and P inverse multiplication, algebraic multiplication of P inverse is what? It become I, and AI is what? A. So we get P inverse A square P. Similarly, we find the D cube, that is D square into D, that P inverse A square P, that is D square, and into D, that is P inverse AP. So again P inverse is become I, and again A square and A become A3. And the similar way we can find the Dn, the nth power of D. So we get what? P inverse A power n P. So here D power n is equal to P inverse n power of A into P. So this is used for the power of matrix. Means if we say, if we find the diagonal matrix of any matrix, then we say, if we want to, if we require to find the A cube A5, so by the help of diagonal matrix we can find A cube A5 and so on. And similarly we can say A inverse A uh, power n is equal to, we can write P inverse D n P. So if we find the diagonal matrix, so easily we can find the power of the or that matrix. Now in that example we discussed, show that the matrix A, that matrix is not diagonalizable. Means we have to discuss in that example, this matrix is diagonalizable or not. So because we have to find the diagonal matrix of that particular matrix, so first we write the characteristic equation of that matrix A is what? We write A minus lambda I determinant is equal to 0. Then we find the eigenvalue for that. So we expand that determinant. So we write lambda. When we expand this, I'm writing that directly the equation 3 lambda square plus 3 lambda minus 1 is equal to 0. And after solve that, we obtain eigenvalues, that is lambda minus 1 is whole cube is equal to 0. That is, we get the lambda is equal to 1 1 1. So here this is what? This is the eigenvalue, or we can say characteristic root. So we have in three eigenvalues of A is what? 1. So we can say 1 is only eigenvalue of A with algebraic multiplicity of 3. Right? Means we have an eigenvalue 1 whose algebraic multiplicity is what? 3, because it repeated 3 times. Now we find the eigenvector corresponding to that eigenvalue. Now we find the eigenvector corresponding to lambda is equal to 1. As you remember, we just write the matrix A minus lambda I, and we write a vector capital X is equal to 0. So here we take lambda is 1. So we write a matrix that is 0, we get minus 1, we take minus 1 1 0 0 minus 1 1 1 minus 3 and 2. We just lambda minus 1. So we get minus 1 on the place of 0, minus 1 on the place that 0, and 3 minus 1, that is 2. And the vector, that is, suppose we say x y z, this, that is capital X vector. This is eigenvector is equal to 0 0 0. Okay, now this is what? This is a homogeneous system, as you remember. So we solve that system. So we convert that system into the that matrix A coefficient matrix into the echelon form and find the rank. So by apply the operation, the first operation, by the help of that element you make that element to 0. So apply the operation on R3 If we add R3 plus R1, so we get minus 1, 1, 0, 0, minus 1, 1. This becomes 0, and minus 3 plus 1 is minus 2, and 2 plus 0 we get 2. X, Y, Z, and this 0, 0, 0. Again, by the help of that element, searching the non-zero element similar way and make that element 0. So apply the operation on R3 again. R3 plus 2 time of, sorry, minus 2 time of, this become minus 2 time of R2. So we get, then we get minus 1, 1, 0, 0, minus 1, 1. This becomes 0, 0, and 0. X, Y, Z, and 0. Now at that state, this convert into the Echelon form. We can say the rank of that coefficient matrix is what? The rank of that matrix is 2. So here we can say the rank of that matrix A is what? 2. So and we convert that at that stage, it converts into the equation. So we can say, how do we write the equation? Now the equation x plus y is equal to 0 and minus y plus z is equal to 0. So we obtain two equations. So the rank of that matrix is 2 and we have a number of unknowns. We have 3. So we can say this system has what? Non-zero solution. So this system has non-zero solution, or we can say non-trivial solution. So here we know we have what? 3 unknown, and rank of the matrix is what? 2. That is, we have two equations. So we can say 3 minus 2 is equal to 1. So here 1 linearly independent solution of that system. Now, and what is that solution? So when we find the solution of these equation, so we just take, we can say y is equal to z, and also from first equation we say y is equal to x. So if we take let y is equal to k, so we can say x and z is also k. So we get a vector. So the eigen vector is what? That we take x, y, z is what? We can say k, k, k. And if we take the k as a common, so we can write 1, 1, 1. So here you have to note that this vector, this is an eigen vector. Therefore, we can say the geometric multiplicity of eigen value is of eigenvalue corresponding to 1, that is 1, is what? Is 1, because we obtain only 1. What? The multiplicity is what? 1, 1, 1. We get k, 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 k. So we can say the geometric multiplicity of the eigenvalue corresponding to eigenvalue 1 is what? 1. So we can what? Here the geometric multiplicity and algebraic multiplicity. So algebraic multiplicity is what? Corresponding to the eigenvalue corresponding eigenvalue is what? Is 3, and the geometric multiplicity is what? Is 1. So which is not equal to, means geometric multiplicity is not equal to algebraic multiplicity. So we can say given matrix is not diagonalizable. Other example is that matrix A is diagonalizable or not. We have to check this matrix is diagonalizable or not. So, and the similar example we discussed previously. So we take the characteristic equation. Characteristic equation, that is A minus lambda I determinant is equal to 0, and when we expand that determinant we get a characteristic equation and find the root of that equation. So we obtain a roots are minus 1 and 3. You can easily find these roots. And then here you have to note that the algebraic multiplicity corresponding to eigenvalue minus 1 is what? Is 2. And for minus or eigenvalue 3 is what? Is 1. So here we find the eigen geometric multiplicity for the eigenvalue minus 1. Then we check is it 2 or not. If it is 2, then matrix is diagonalizable, otherwise not. So we find what? The eigenvector corresponding to eigenvalue. First we find the corresponding to eigenvalue lambda is equal to minus 1. Now we find the eigenvector, that is we write A minus lambda I. We write a vector that say x1 corresponding to minus 1, 0. Now when we put the lambda is equal to minus 1, so we obtain a matrix. Coefficient matrix we get 8 4 4 minus 8 4 4 minus 16 4, sorry 8 and 8, and we write a vector says x y z is equal to 0 0 0. So here you have to see that this coefficient matrix, the row 3, row 1 and 2 are similar, so we apply the operation on r3 minus 2 time of r1, and on r2 we apply r2 minus r1. So we get minus 8 4 4 0 0 0 0 0 0 x y z. So this is what? This is a homogeneous system. Now it's reduced in the Hecklin form, and we can say the rank of that matrix is what? Rank of that coefficient matrix is what? Is 1. Here at that stage we convert into the equation. So we get on a single equation, that is minus 8x plus 4y plus 4z is equal to 0. So here we can say this system is what? Rank is 1, and there are 3 unknowns. We have 3 unknowns x, y, z. So rank is less than the number of unknown, so we get a non-trivial solution. Or we can also say, so the given system has what? 3 minus 1, that is 2 linearly independent solutions. So we have two linearly independent solutions corresponding to that. And what are these solutions? So these two solutions is obtained by putting z is equal to 0 and we can say y is equal to 0 in that equation. So first we take the z is equal to 0. So what we get? Minus 8x plus 4y y is equal to 0, and when we put y is equal to 0, so we get minus 8x plus 4z is equal to 0. So in that, by that equation we get 2x is equal to y, and here we get 2x is equal to z, right? So in that case, what we get the solution, if we take, let y is equal to k, so if we take let y is equal to k in that condition, so we can say x is equal to k by 2, y is equal to k, and z is equal to 0. Here you also take the x is equal to k. If you take the x is equal to k, so it is easy to remember. So x is k and y we can say 2k. It's easy to define. So what is that vector? Now the vector is k, k, sorry, 2k and 0. And if we take y is equal to 0, and at that let x is equal to k, so we get z is equal to 2k and y is equal to 0. So we get another vector, that is k, 0, 2k. If we take k as a common, so we get 1, 2, 0. In that case, if we take k as a common, 1, 0, 2. So here, so one of independent vector, we can say that is x1 is what is k, 2k and 0, or we can say 1, 2, 0. And the other, the second independent vector we obtain corresponding to the lambda is equal to minus 1 is what, k, 0, 2k. So here k, 1, 0, 2. So here x1 and x1 dash are two Li linearly independent vectors for lambda is equal to minus 1. So the geometric multiplicity of the lambda is equal to minus 1 is what? Is 2, which is what? Equal to algebraic multiplicity of lambda is equal to minus 1, that is also 2, as we discussed in the starting of that example. So we can say the matrix, given matrix, is diagonalizable. Okay class, remaining part we discuss in the next lecture. Thank you.